Okay, week 1 we learned about electric force, week 2 electric field, and now week 3 we're going to learn about electric flux. So last week we talked about fields in general, scalar fields, vector fields, different kinds of fields. Let's start with the general idea of this word flux. So in the most general sense, the word flux refers to flow. And so we could have a flow or a flux of fluid through a pipe, or the flux of water through a river. Heat flows through conductors. We could want to measure the flux of heat through a conductor. Sunlight flows out through space. What's the flux of sunlight arriving at the Earth? A radioactive material emits radiation. What's the flux of radiation that hits a person who's standing near the radioactive material? So those are all examples of the flow of something through space, and how do we measure it? So I'm going to focus first on this concept of sunlight and measuring the flux of sunlight at the Earth. Let's do that. Okay, here's a diagram of the sun's energy, or the solar flux, arriving at the surface of the Earth. Notice the first thing that happens is it comes to the atmosphere and then has to pass through the atmosphere. And as you might guess, some of that energy is going to be absorbed by the atmosphere. So if you look up solar flux, this is what you'll find. So the number given for solar flux is 1373 watts per square meter, arriving from the sun at the atmosphere. So I'm rounding that to 1400 watts per square meter. And even on a clear day, not more than 75 or 80% gets through. Let's use the rounded number of 1000 watts per square meter will arrive at the surface of the Earth, the solar flux at the surface of the Earth on a relatively clear day. So before we go further, let's understand this unit, watts per square meter. So the amount of energy received is going to depend on the area. Obviously, a bigger area will receive more energy, and so that's why this is here. So to get the energy, or actually, what is a watt? Look up a watt and write down what a watt is, and then come and tell me. Okay, so what you found or remembered, if you're good, is that a watt is a unit of power. We use the symbol P, and it's energy per unit time. It's the rate at which energy arrives, right? Obviously, a longer period of time will be more energy. So we rate the flow of energy from the sun. It makes sense to put it in terms of watt per square meter, or what's arriving at the surface of the Earth is this. Okay, given that, supposing we have a solar collector. So our collector is 100 centimeters long by 50 centimeters wide. And first question is, how much solar flux in terms of watts of power arrives at this collector? And if it collects with an efficiency of 20%, how much power is actually captured from the sun? So those are two questions. Do those calculations and come back. Okay, what you should have gotten is, since this is a half a meter in area, it's going to about 500 watts is going to arrive, right? Because we have 1000 watts per square meter times 0.5 meters squared, and the meters cancel, and so you get 500 watts of solar flux lands on the collector. 20% efficiency, 100 watts is collected. How much energy is that? Well, it depends on, right, the time. If the collector in 1 second will collect 100 joules, in 10 seconds it'll collect 1,000 joules, and so on. So that's how that works with solar flux. But wait, we ignored one thing. If I take this panel and I put it in the sunlight, it also depends on how I position the panel, right? So if I position the panel so it directly faces the sunlight, then yes, I will get this. But supposing I put it in an angle, supposing instead this is fixed in place and it happens to be at 45 degrees, then how much solar flux in terms of watts will land on it and how much will it collect? I'm at 45 degrees. Let me draw that. So here's the panel at 45 degrees to the sunlight. It's 2 dimensions, so you have to... But the way that we're going to specify the direction of the panel is by a normal to the surface, a perpendicular or normal to the surface. In other words, the direction of an area or any area element is the direction it's facing. So, right, if we want to get the maximum solar flux, we want to face it toward the sunlight so that the angle, we're not going to read the angle to the surface, we're going to read the angle to the normal. This is the convention. You have to learn this. So in this case, the angle is going to be 45 degrees either way. But in this case, this is the 45-degree angle we want. And so at this 45-degree angle, now answer the question, how much solar flux in terms of watts is going to hit the collector and how much is actually going to be collected? See if you can figure that out. I'll give you a hint. It's a vector problem. So in case you're stuck, here's a hint. Let me draw a vector. This vector here is the solar flux vector. And if we take our axis along the area, it has, the solar flux has a component that's along that area vector and another component which is parallel to that. So this part of the flux is what's going to hit directly onto the plate, and this part of the flux is just going to miss the plate entirely because it's parallel to the surface. And since this angle is 45 degrees, we want to use, to get this part, right, this component, the one that's going directly, the part of the sunlight that's hitting the solar panel directly is this. This is the part of the sunlight that's missing it, these vector components. So we want, this is adjacent, so we want the cosine of 45 degrees. So now solve the problem. So what you should have gotten is the 1,000 watts times the half per square meter times the 1/2 meter squared gave us the 500, but since we're at an angle we had to multiply by the cosine of 45 degrees. That gives us 354 watts. And since the solar panel only collects, that's what lands on the panel, only collects 20%, we're collecting 71 watts instead of, I erased it, 100 watts. In other words, our the amount of energy we're collecting is only 70% of what we were collecting if we were at an angle where the solar panel faced directly into the sunlight. And that leads to that, before we leave this diagram, we can understand why areas of land around the equator or places that are facing directly into the sun are going to collect more solar flux than areas which are at a steep angle to the solar radiation toward the poles. There's also the factor, just while we're here, of the distance of atmosphere it's passing through. And so the same area of land is going to collect less energy than the same area here. and also that 1,000 watts that arrived at the surface, it might only be 800 watts here because of the thicker distance of atmosphere it has to pass through. Okay, now let me just summarize. So the flux depends on the intensity of the sunlight, the area of the collector, and the cosine of the angle between these two vectors. So with that in mind, let's go and talk about electric flux. Okay, switching from sunlight to electric fields, a few things to remind ourselves. First of all, since for simplicity, we like to have uniform electric fields where the lines aren't spreading out and are uniformly spaced, and we create that situation by two charged parallel plates, so that inside or between the plates we get a uniform electric field. That means that the field strength isn't varying as we go to different points between the plates. So this is physically how we create a uniform electric field. The other thing to keep in mind is that the field lines are shown as arrows, so it looks like a flow of something, but it's static. So don't forget that the electric field is static. It's not like the sunlight. It's not actually flowing, but we use the same idea to talk about electric flux. So here I am trying to draw this in 3 dimensions. 2 parallel plates and the field between them uniform. Okay? Okay, so here we are. Electric flux. We use this uppercase phi, the Greek letter phi, and we often put a subscript e so we know it's electric flux. And it depends on 3 things. It depends on the strength of the electric field, it depends on the area over which the electric field is passing, and it depends on the angle between the normal vector to the area and the direction of the field. So this angle theta will take the cosine of that angle to get the total electric flux. Now in this case you see the electric field is uniform. We explained that. And so we just calculate the flux. So let me give you a problem. We have a square which is 10 centimeters on a side, and we have an electric field which is 400 newtons per coulomb, and we have an angle which is 30 degrees. Calculate the electric flux passing onto, or in this case, through that surface element that you see. Go ahead, calculate it. So this is what you should have gotten using the equation. We write the E, the A. I hope you changed it to meters. If not, you would have centimeters in your units. That would be not the convention, but it would be correct. But I changed it to meters because this is the standard units of flux. So 400 newtons per coulombs times 0.1 meters squared, that's the area, times the cosine of the angle between the field and the normal to the area, 30 degrees, and I get 3.64. Rounding to 2 significant figures, I get 3.5 newtons times meters squared per coulomb. Those are the units of flux. It does have a name, but we don't use it. We're just going to leave it in these units. So that's how we calculate electric flux for a simple situation where the field is uniform and the area element is flat, and so the angle is constant. In some cases, it won't be so simple. Okay, this looks like the sunlight hitting the earth, but we could think of it as a uniform electric field passing onto a spherical conductor. And what you'll notice here is that although the field is uniform, it's hitting the conductor at different places at different angles. So if we take an area element here, it's hitting directly on that area element. Whereas if we take an area element here, it's hitting at an angle to that area element. And if we take an area element here, there's no flux hitting it, right? It's passing right over it because the angle would be 90 degrees and the cosine of 90 is 0. So you're going to get more flux per unit area here than you will here because of the angle. And so the way to solve this problem is you have to do an integral. And so let me show you what that looks like. So in the most general case, where either the strength of the field in magnitude and direction is changing so that the angle between the field and the area element varies from area element to area element, right? Then you have to do an integral. And so the most general definition of electric flux is really a surface integral of electric flux is the surface integral of E cosine of theta dA, where the cosine is the angle between the E vector and the A vector. Actually, this has a Calc 3 shorthand notation. We talked about the dot product before. So the most general and condensed form of electric flux is the surface integral of vector E dot product vector A. You'll see this. We saw this when we defined work, right? Similar, a line integral, and we'll see it throughout this semester, and it shows up in Calc 3. That's the most general definition of flux. That's what it looks like. And in the simple cases, almost all the problems we do, we can just do EA cosine theta when the E and the theta are constant over the surface.